The facility ought to have been a cacophony of noise. A processing plant of this scale, handling raw aggregate, would normally produce a vibration that resonated deep in your molars. In its place, the quiet was profound, punctuated only by the whisper of cooling fans on a generator that had gone cold. For every hour the main turbines remained offline, the company's ledger hemorrhaged $58,000. Around the inert Tier 4 unit, 3 technicians huddled, their gazes fixed on a laptop screen that displayed no answers. A lone DPF differential pressure sensor had malfunctioned, effectively turning the $250,000 machine into a brick. It was an error of logic, a phantom in the code summoned by a failure in the physical world. Marina paid no mind to the white plastic housing and made her way toward a shadowed recess of the maintenance bay. The atmosphere grew denser as she passed into the storage annex. The sterile, biting aroma of electrical ozone and cleaning agents dissipated, supplanted by the deep, loamy perfume of antiquated machinery, a concoction of settled dust, iron oxide, and hydraulic fluid that had cured into a permanent lacquer on the concrete. It was the scent of industry from before it had been sanitized. This was the boneyard, the forgotten corner where management exiled equipment that could no longer interface with their digital command centers. They referred to it as junk storage. Marina considered it her reserve arsenal. In the heart of the gloom, concealed beneath a tarp made rigid with filth, was the silhouette she had come for. The tarp was heavy, oil-soaked canvas, a far cry from the flimsy blue polyethylene of today. She took hold of the fabric's edge and heaved. The weighty cover slid aside, exposing the 12V71. The sight of it was a jolt to the senses. The engine was an immense block of cast iron, its peeling alpine green paint a testament to its age, resting on a skid that seemed to buckle beneath its sheer mass. It was a Detroit diesel, a 2-cycle titan from a time when engineers valued structural heft over power-to-weight ratios. There were no plastic shrouds to conceal the valve train. No complex wiring harnesses were draped across the intake manifold. There was only iron, steel, and the stark honesty of mechanical connections. In the valley formed by the V-block sat the roots-type blower, the mechanical lungs that were the very definition of this machine's respiration. She noted the absence of rust on its casing. Aluminum does not rust. It merely oxidizes. One of the technicians from the main bay ambled over, his tablet casting a blue luminescence in the dimness. He glanced at the weeping seals and the caked-on layers of grime, then tapped his screen to display a void where the engine's data should have been. In his view, a machine lacking a diagnostic port was effectively mute. He saw a heap of scrap iron that would probably seize the instant its crankshaft attempted to turn. Marina did not look up from her work. Her eyes were tracing the path of the fuel lines. She understood what he perceived, a machine incapable of reporting its own ailments. But this engine had no need to speak with a computer, for it communicated in an entirely different dialect. It was forged when heavy was considered a safety margin, not a detriment to efficiency. She reached out, placing her palm firmly against the valve cover. Beneath the oxidation, the iron felt impossibly dense. It did not feel inert. It felt as if it were merely waiting. She finally met the technician's gaze. "You keep an eye on the screen," she stated. "I'll handle the real iron." Marina did not reach for her tool bag right away. Diagnosing a machine of this era didn't begin with a wrench. It began with a physical assessment. She approached the engine block like a medic, triaging a casualty, her hands moving along the cold flanks of its V-shaped configuration. Her fingertips followed the contours of the valve covers, searching for the telltale crust of old oil leaks that had hardened into a geological stratum. The gaskets were made of cork, not the advanced silicone or molded rubber the technicians in the other bay were accustomed to. Cork desiccates, contracts, and turns fragile over decades, transforming from a seal into a sieve. She pressed her thumbnail into the exposed section of a coolant hose. It was as hard as stone, petrified by countless heat cycles and the passage of time. It didn't compress. It chipped away. This was her first piece of data. Every rubber component on this skid was long dead. She proceeded to the accessory drive. The belts hung with a slack, weary exhaustion, but when she gave one a twist, she felt the internal cords give way with a snap. Dry rot had consumed them. The alternator's pulley was frozen solid. seized by oxidation within its bearings. These were superficial injuries, however, and irrelevant to the fundamental health of the block. The part-swapping technician lingered behind her, his diagnostic tablet held before him like a talisman. He observed her touching the metal, perplexed by her unstructured methodology. He inquired if she needed a multimeter. Marina dismissed him and reached for the dipstick. This was the equivalent of drawing blood. She extracted the long steel ribbon from its tube. The oil clinging to it was viscous, black, and as opaque as ink. She didn't wipe it clean immediately. Instead, she took a drop and rubbed it between her thumb and forefinger, feeling for any abrasive texture. There was no granular friction, no shimmering metallic particles that would signal a destroyed bearing or a disintegrating camshaft lobe. The oil was perfectly smooth. Its blackness was merely soot, carbon held in suspension. This indicated that 30 years prior, when the engine last operated, the oil's dispersant additives were still effective. It told her the machine had been properly shut down, not catastrophically killed. "It's filthy," the technician commented, his nose wrinkling at the aroma of antique diesel and sulfur. "It's truthful," Marina retorted. "It provides a history. Your sensors can only report the immediate present." She wiped the dipstick clean and reinserted it to check the level. It was full. There were no water beads on the tip, which suggested the cylinder liner seals had not failed during its long slumber. Coolant had not seeped into the crankcase. The block itself was most likely sound. But fluid levels were merely passive information. She needed to feel for active resistance. Reaching into her bag, she produced a 24-inch breaker bar and a socket that fit the crankshaft bolt. "You're going to snap a bolt," the technician cautioned. "You can't just apply force like that." "I'm not applying force," she replied, seating the socket onto the bolt. "I'm asking it a question." She put her weight into the bar. The initial pushback was absolute. The static friction built up over 3 decades of stillness. The piston rings were surely dry, bonded to the cylinder walls with a grip that verged on a chemical weld. She didn't jerk the bar. She applied a smooth, hydraulic pressure that originated from her shoulders. She closed her eyes, concentrating solely on the feedback that traveled up the steel handle into her hands. A deep groan emanated from the engine, the sound of metal protesting against metal, followed by an abrupt release. The crankshaft began to rotate. She didn't pause. She maintained a fluid motion, guiding the entire assembly through its cycle. She was feeling for any soft spots in the compression, cylinders that offered no pushback, which would indicate stuck valves or broken rings. But as she turned it over, she felt the rhythmic, powerful resistance of air being compressed. 1 cylinder, then 2, then 3. The engine was pushing back against her, which meant it was still alive. Then, the bar came to a dead stop. It wasn't the soft resistance of compression. It was a hard, unyielding mechanical block, a wall of metal. The technician let out a scoff. "Seized," he declared. "I knew it. It's just a boat anchor." Marina kept the tension on the bar. She did not release it. She could discern the difference between a seized piston and a component that was merely stuck. A seized engine feels like a single, solid piece of fused metal. This felt like something had snagged. She gently rocked the bar, back and forth, listening intently. A faint click echoed from the top of the right bank. It wasn't a connecting rod. It was a valve, an exhaust valve, most likely glued in its guide by old carbon deposits, hanging open and making contact with the piston. It was a well-known affliction of the 12V71, a machine equipped with 24 exhaust valves and no intake valves at all. "It's not seized," she stated, visualizing the internal geometry in her mind. "It's just a little stiff." She applied a fraction more torque, and with a sharp pop, the obstruction gave way. The valve snapped shut as its spring overcame the varnish. The engine rotated freely once more, the heavy flywheel now carrying the momentum. She had confirmed that the bottom end was free. The pistons were moving. The crank was straight. The heart of the machine was viable, but now she had to inspect its lungs. She looked up at the air intake system, the massive ductwork that fed the central blower. That was where the true peril often lurked. Not in the iron itself, but in what the iron had breathed in during its long sleep. Marina shifted her focus to the enormous aluminum casting that held court in the valley between the 2 cylinder banks. For an amateur, it resembled a supercharger added for performance, a hot rod component that seemed out of place on an industrial generator. The technician, still hovering nearby with his ineffective tablet, pointed a spotless finger at it. "Is that the turbocharger?" he inquired. It was the type of question that revealed a fundamental void in his training, a void carved out by decades of four-stroke dominance. "It's a blower," Marina corrected him. "And without it, this engine is nothing more than 3,000 pounds of scrap metal. It uses this to breathe." The 12V71 was a two-stroke diesel. Every time a piston reached the apex of its stroke, it fired. There was no wasted movement, no dead revolution dedicated to clearing the chamber. This efficiency, however, came at a mechanical price. The piston never moved downward just to draw in air. It was incapable of inhaling on its own. It had to be force-fed. "This is a positive displacement pump," she explained, tapping the aluminum casing. "A Roots type. It shoves air into the cylinders at a fixed volume. When the piston descends, it uncovers ports in the cylinder liner, essentially holes in the wall. This blower forces fresh air in through those holes, which in turn pushes the exhaust gases out through the valves in the head. The process is called scavenging. If this blower ever stops, the engine will instantly suffocate." She took hold of the heavy steel clamp that fastened the main intake pipe to the blower's inlet. The rubber boot was rigid, fighting her grip. This was the critical moment for any engine resurrection. The modern technician would check air filters by glancing at a restriction indicator on a dashboard. Marina checked them by physically breaching the intake system. Attempting to start a dormant engine without first inspecting its throat was a gamble against the entire rotating assembly. She loosened the bolt and, using a flathead screwdriver, pried the rubber boot free. It gave way with a sound of tearing. She moved the heavy steel pipe aside and aimed her flashlight into the blower's gaping maw. The technician recoiled. "What is all that?" "That," Marina said, her gloved hand reaching inside, "is precisely why we don't just hit the start button." Wedged tightly within the intake, pressed directly against the blower's rotors, was a thick, fibrous clump. It was a marvel of rodent engineering, a mix of shredded insulation, old newspaper, dried plant matter, and the skeletal remnants of a mouse that had died long ago. It was a mouse nest, the silent executioner of barn-find engines. "If we had tried to crank it," she elucidated, pulling the mass out in chunks, "the vacuum would have ingested this entire wad of garbage into the rotors in less than a second." She cleared away the debris, uncovering the two long, helical aluminum rotors that lay beneath. They were stunning, machined with a level of precision that contradicted the engine's brutish reputation. They spun with clearances measured in thousandths of an inch. They never touched each other, nor did they touch the housing, but their proximity was close enough to trap air molecules. "These rotors spin at double the engine's speed," she stated, wiping the aluminum surface with a clean cloth. "If that mouse nest had been pulled through, it would have jammed the lobes. The drive shaft would have sheared off, or the housing would have cracked. Your sensor would have flagged a mass airflow error long after the engine had already torn itself apart." She examined the lobes for any signs of pitting. They were a dull gray, but perfectly smooth. There was no scoring, no corrosion. The aluminum had withstood the moisture from the nest. She reached in and gave one rotor a push with her thumb. It turned. The movement was smooth, heavy, and silent. The gears at the rear of the blower meshed flawlessly. "This is what makes all the noise," she said, pulling her hand out. The technician looked puzzled. He was familiar with the whistle of turbochargers. "This doesn't whistle," she warned him. "It screams. When this machine is running at full capacity, these rotors are slicing through the air thousands of times a minute. It generates a harmonic resonance, a shriek. It isn't a flaw. It's the sound of raw efficiency. It's the sound of an engine that fires on every single revolution." She started to reassemble the intake, leaving the piping disconnected for the moment, so the engine could breathe unrestricted during its initial crank. The lungs were clear. The airway was open. The machine was capable of breathing, but breathing was only one part of the equation. Now she needed to address the fuel, and on a Detroit diesel, the fuel system was where the true dark arts resided. With the airway now clear, Marina focused her efforts on the heart of the machine. On a contemporary diesel, the fuel system is a complex network of high-pressure common rails and piezoelectric injectors governed by microprocessors. A design philosophy centered on self-preservation, where the ECU will shut down the engine to protect itself. The 12V71, however, was built with a philosophy of mission preservation. Marina reached for the heavy steel latches on the valve covers, popping them open to expose the right bank of cylinders. The scent of old oil was more pungent here, laced with the acrid tang of ancient diesel fuel. The technician leaned closer, the beam of his flashlight cutting across the exposed valve train. He flinched slightly at the sheer visual complexity. For eyes accustomed to the sterile, plastic-shrouded cylinder heads of the 21st century, a Detroit head resembles the aftermath of an explosion in a typewriter factory. Each cylinder had 4 exhaust valves, linked together in pairs, but it was the third rocker arm, situated in the middle of each set, that held the key. "Where are the high-pressure fuel lines?" the technician asked, searching for the familiar steel plumbing that defined his expertise. "There are none," Marina replied, using a rag to wipe a rocker arm clean for inspection. "This is a unit injector system. It's the very reason this engine will still be operational when your Tier 4 generator is being melted down for scrap." She indicated the injector, positioned dead center in the cylinder head. It didn't resemble a fragile electronic device. It looked more like a hydraulic press. She began to explain the brilliance of the design. In this engine, fuel is circulated at a leisurely 50 psi, barely enough pressure to inflate a bicycle tire. It travels through galleries drilled directly into the cylinder head, which keeps the injectors cool. There is no bomb of high-pressure fuel waiting to rupture a seal. The pressure is generated only at the precise moment it's needed, right within the injector itself. "Do you see that middle rocker arm?" she inquired, pointing to the massive cast-iron lever. "It's actuated by the camshaft. As the piston rises on its compression stroke, that rocker arm slams down on the injector plunger. It instantly creates 20,000 psi right at the nozzle tip. There are no pumps to time, no computers to send a signal to a solenoid. It's just a cam lobe striking a roller." This was the system's mechanical advantage. In a modern engine, if the single high-pressure pump fails, the entire engine is dead. In a Detroit, each cylinder functions as its own independent power station. If one injector becomes clogged or fails, the other 11 simply carry the load. The engine doesn't shut down, it just gets angrier. Marina retrieved a specialized tool from her bag, a timing gauge. It wasn't a dial indicator or a digital device. It was a simple, machined pin stamped with 1.460. This was the only computer the engine required. She slid the pin between the injector follower and the body to check the height. This simple action set the timing of the fuel injection. If the pin created a slight drag as she passed it through the gap, the timing was perfect. She checked the first cylinder. A slight drag. The second cylinder. Drag. The third. Drag. The lash settings had not shifted in 30 years. The lock nuts remained tight, the push rods perfectly straight. The technician stared at the simple metal pin, then glanced back at his tablet. He was attempting to reconcile the stark simplicity with the inherent violence of the machine. "But how do you tune it?" he asked. "Where's the fuel map? How does it determine how much fuel to inject based on the load?" Marina withdrew the gauge and pointed to a steel tube that ran the length of the cylinder head, connected to each injector by a series of small, intricate linkages. "That is the map," she declared. "It's called the control rack, and at this moment, it's the one thing that could kill us." Marina reached into the cylinder head and took hold of the control tube with her gloved fingers. She attempted to rotate it. It was completely solid. It felt as if it had been welded to its stanchions. This was the most perilous state a Detroit diesel could be in. In a gasoline engine, you regulate speed by restricting the air. If the throttle gets stuck open, you can simply cut the ignition. But a diesel engine always has an excess of air, enough to tear itself apart. It operates unthrottled. The only thing preventing it from self-destructing is the precise metering of fuel. And the only thing metering that fuel was this steel tube, which was currently cemented in place by 3 decades of polymerized diesel varnish. "It's stuck," she said, her voice dropping a full octave. "If we had tried to start this engine 5 minutes ago, we would all be running for the exit right now." The technician looked at the frozen linkage. "Why? It would just rev high, wouldn't it?" "It would run away," Marina corrected him. "If this rack is seized in the full fuel position, the engine will start to accelerate. The governor will attempt to pull it back, but the linkage won't budge. The RPMs will climb past 2,000, then past 2,500. The governor weights will be screaming for it to stop, but the rack will be deaf to them. It will continue to accelerate until the valves float, the connecting rods stretch, and the flywheel makes a high-speed exit through the housing. It doesn't just fail, it detonates. She reached for a can of potent solvent. This was the surgical phase. She sprayed the clevis pins and the small gears that connected the rack to each injector. The sharp smell of the solvent mingled with the old oil, creating a chemical haze in the confined space. She didn't try to force the tube. You never force the rack. If you bend it, the cylinders become imbalanced, with one fighting against another. You have to gently persuade it. She worked the mechanism back and forth, feeling the microscopic layers of varnish begin to dissolve under the combined effects of the chemistry and the friction. The governor is the brain, she explained, working the solvent into the pivot points. But it's not a computer. It's a set of flyweights spinning on a shaft. As the speed increases, centrifugal force pushes them outward, and that force works against a spring to pull this rack back. It's a physical contest between the engine's energy and the tension of a spring. It's analog computing in its purest form. It responds to physics, not to code. Abruptly, the resistance gave way. The rack snapped back under the tension of its return spring. Click. She pushed it to the full fuel position. Clack. She released it. Click. That, she said, repeating the motion again. Clack, click. Clack, click. That is the sound of safety. If you don't hear that distinct metallic snap, you do not touch the starter. She moved to the governor housing itself. A small screw, secured by a jam nut, protruded from the casing. This was the buffer screw. It was a minute adjustment that baffled modern mechanics, who were used to dealing with idle air control valves. This engine breathes, she said, loosening the jam nut. When you remove a load from a mechanical diesel, the governor cuts the fuel to slow it down. But sometimes it cuts too much, and the engine stalls. This screw acts as a cushion. It catches the rack just before it dies, gently nudging it back toward idle. She explained the phenomenon of hunting. A digital engine maintains a perfectly flat, unwavering RPM because a computer makes micro-adjustments faster than the engine can react. It produces a monotonous drone. A mechanical governor, on the other hand, hunts. It actively searches for equilibrium. You can hear the engine breathing, its RPMs rising and falling slightly as the flyweights battle the springs. It sounds alive because it is responding to the world in real time, not just predicting it based on a pre-programmed lookup table. We want it to hunt a little, she said, setting the screw by feel, estimating the correct tension. A hunting engine is a free engine. A perfectly steady one is often on the verge of binding. She cycled the rack one last time. It moved with the satisfying smoothness of a rifle bolt. The nervous system had been restored. The brain could now communicate with the muscle. The danger of a runaway had been averted, but the machine was still just a collection of individual moving parts. She had verified the blood, the lungs, the heart, and the nerves. Now, she had to inspect the bones. She wiped the solvent from her hands and looked down at the massive cast iron block itself. The rack would control the explosions, but the block had to be strong enough to contain them. Marina wiped the solvent from her gloves and placed her hand on the flank of the engine block. To an untrained observer, it was merely a dirty piece of metal. But for a specialist, this particular casting was a resource more precious than gold. It was high-nickel gray iron, poured in a foundry that had likely ceased to exist, during a period when material cost was of secondary importance to structural integrity. The technician tapped his foot, growing impatient. He saw the surface rust and wrongly assumed the metal was compromised. He failed to understand that cast iron is like concrete. It doesn't weaken with age, it matures. She explained the concept of seasoning to him, though the vacant look in his eyes indicated the metallurgy was going over his head. When a complex form like a V12 block is cast, the cooling process traps immense internal thermal stresses. A new block is essentially alive. It has a tendency to twist and warp as it heats and cools. Modern manufacturers attempt to artificially age their iron using stress relief ovens, but you cannot manufacture time. This block had endured thousands of heat cycles and then sat undisturbed for 3 decades. The internal stresses had long since equalized, the molecular lattice settling into a state of permanent stability. It was dimensionally sound in a way that a modern aluminum block, fresh from a high-pressure die mold, could never be. You could bore this block, hone it, and run it at maximum load, and it wouldn't shift by 1/1000th of an inch. It was a seasoned anvil. But the true brilliance of the Detroit design wasn't just the iron. It was the holes within the iron. She pointed to the cylinder decks. "This is a wet sleeve engine," she stated. "That means the pistons never actually touch this block." In the technician's world of disposable aluminum engines, the cylinder bores are either plated directly onto the block material or use thin, dry sleeves pressed in with interference fits. If a piston scores the cylinder wall in a modern block, the engine is often declared scrap. It becomes a $200,000 mistake caused by a $10 ring failure. Here, the cylinder is a distinct component, a hardened steel liner that slides into the block and is sealed by O-rings. It is suspended in the coolant, completely surrounded by water for maximum heat transfer. "If this engine were to blow a cylinder," Marina said, tracing the outline of where a liner was seated deep inside, "I wouldn't need a crane. I wouldn't need a machine shop. I would pull the head, slide the old liner out, drop in a new kit, and have it running again in 4 hours. This engine is not a single fused unit. It's a reusable chassis for consumable parts. It is infinitely rebuildable." This was the fundamental distinction between a consumer product and an industrial tool. One was engineered to be consumed. The other was engineered to be maintained. She inspected the weep holes on the side of the block, located just above the oil pan rail. These were the telltales for the liner seals. If the O-rings at the bottom of the sleeves had failed, coolant would be dripping from here, or worse, silently migrating into the oil. The holes were completely dry. The rubber seals, shielded from light and oxygen within the dark iron, had retained their tension. The water jacket was secure. The block was sound. 3,000 pounds of iron is more than just weight to be carried. It serves as a thermal battery and a vibration damper. A diesel explosion is a violent hammer blow. A lightweight aluminum block rings like a bell under that stress. It flexes, and that flexing kills main bearings. This mass absorbs the violence. It soaks up the heat of a sudden load spike without overheating. It doesn't notice the vibration because it is simply too heavy to be moved by it. It was constructed with a factor of safety that modern engineering has systematically optimized out of existence. The weight wasn't a penalty. It was the insurance policy. The quiet in the maintenance bay was shattered by the sound of heavy boots on concrete and the sharp, panicked voice of the facility manager. He was not concerned with metallurgy or history. He was concerned that the main breaker was still open and the site was losing $58,000 every 60 minutes. He glanced at the dismantled Tier 4 generator, then at the pile of grease-caked iron that Marina was standing over. He asked if this was some kind of joke. He saw a museum relic. Marina saw the only viable solution left in the building. She didn't bother wasting time explaining the physics. She just pointed to the heavy-gauge jumper cables coiled on the floor. "Get me 24 volts," she commanded, "and stand clear." The technicians scrambled to drag over a cart of 8D batteries, massive lead-acid bricks, each weighing as much as a transmission. This was not a simple matter of plugging in a laptop charger. To awaken a 12-volt 71 from a 30-year slumber, you needed enough amperage to weld steel. She connected the cables in series, the heavy copper clamps biting into the lead terminals. A spark erupted, a sharp crack of electricity finding its ground, and the smell of ozone mingled with the stagnant air. There was no start button. There was no key to turn. On an industrial skid of this type, the starter solenoid was often engaged directly at the motor, or through a heavy-duty toggle switch that bypassed all safety systems. Marina found the starter, a massive Delco Remy unit the size of a loaf of bread, bolted to the side of the flywheel housing. She looked at the technicians. They had backed away to the doorway, instinctively sensing that something violent was about to occur. They were accustomed to enclosed, soundproofed generators that produced a gentle hum. They were not prepared for the mechanical brutality of an open-engine cold start. "Clear the prop wash," she called out, checking the line of fire for the massive cooling fan. She engaged the solenoid. The sound was not a whir. It was a deep groan. Rug. Rug. The massive electric motor slammed its pinion gear into the flywheel's ring gear, dumping hundreds of amps into the circuit. The lights in the shed dimmed noticeably as the starter battled the static friction of 12 pistons, 24 compression rings, and 3 decades of gravitational pull. The engine turned over slowly, laboriously. It sounded like a giant gasping for air. Whoom, whoom, whoom. The oil pressure gauge remained flat. The fuel lines were still dry. The engine was spinning on nothing but residual oil film and hope. After 10 seconds of continuous cranking, the starter motor began to heat up, the acrid smell of burning varnish rising from its windings. The engine wasn't catching. It was just acting as an air compressor, pumping cold atmosphere through cold iron. One of the technicians stepped forward, holding a red can with a yellow cap. Starting fluid. Ether. The so-called mechanic in a can. He reached toward the open air intake. "Don't you even think about it," Marina barked, her voice slicing through the sound of the cranking. "It needs help," he shouted back. "It's too cold." "That's not help, that's murder," she yelled in return. She knew exactly what ether did to these engines. It was a highly volatile hydrocarbon that ignited far too early in the compression stroke. It didn't push the piston down. It struck the rising piston like a sledgehammer. It shattered ringlands. It bent connecting rods. It cracked cylinder heads. It was also an addiction. Once an engine was started on ether, the rings would often be damaged just enough that it would only ever start on ether again. "We do this firmly," she said, "or we don't do it at all." She reached for the control rack she had just freed. This was the moment the human operator became the engine control unit. In a modern vehicle, the computer determines how much fuel to inject during cranking based on coolant temperature and barometric pressure. Here, Marina was the computer. She had to feel the engine's hunger. She pushed the rack to the full fuel position, flooding the injectors, then pulled it back to half as the cranking speed slowly increased. She was manually modulating the injection pulse width. She listened to the rhythm of the exhaust. Chuff, chuff, chuff. It was still just pumping air. Then she saw it. A faint puff of white haze drifting from the exhaust manifold. White smoke is raw, atomized diesel fuel that has been heated but is not yet ignited. It is the first sign of life. It means the injectors are popping. It means fuel is entering the cylinder. It just needed a few more degrees of heat to reach its flash point. The act of compression was building heat in the iron. The sheer friction was warming the cylinder liners. She held the starter button down, ignoring the heat now radiating from the motor. You had to commit. If you stopped now, the heat would dissipate, and you would lose. The white smoke grew thicker, stinging the eyes and filling the shed with a cloud of unburnt hydrocarbons. The engine began to cough now, stumbling, trying to find its rhythm. The white smoke was becoming blinding. And then, for a fraction of a second, the color changed. A single pulse of black. Combustion. That single puff of black smoke was the herald. It signified that the physics had finally tipped in their favor. The heat generated by the pistons compressing air to 1/18 of its original volume had surpassed the auto-ignition temperature of the fuel inside the cylinders. The reaction was instantaneous and violent. The starter motor whined, suddenly relieved of its immense burden as the heavy flywheel's momentum overtook the pinion gear. The Bendix drive kicked back with a sharp metallic clack, disengaging the electric motor, and suddenly, the only thing turning that 3,000-pound assembly was the controlled explosion of diesel fuel. It did not purr. A 1.2 V71 doesn't idle. It seethes. The transition from silence to operation was less like starting an engine and more like a contained detonation. One cylinder fired, a sharp cracking report that ricocheted off the corrugated metal walls of the shed like a gunshot. Then 3 more. Then 6. And then, in a thunderous cascade of noise that vibrated the concrete floor beneath their feet, all 12 cylinders caught fire in unison. The sound was deafening. It wasn't the low-frequency rumble of a 4-stroke Cummins or Caterpillar that the modern technicians were familiar with. This was a 2-stroke cycle. Every time a piston reached the top of its liner, it fired. At 1800 RPM, this machine was producing 360 power strokes every single second. The frequency merged into a single, terrifying, continuous tone, the infamous Detroit scream. The needle on the mechanical tachometer swept upward with alarming speed. This was the danger zone. The cold, thick oil in the governor housing was delaying the flyweights from moving outward to pull back the fuel. The engine wanted to run. It wanted to consume every last drop of fuel the injectors could provide. The roar's pitch shifted higher, climbing past 1,200, past 1,500, aiming straight for the red line. The technicians scrambled backward, their hands clamped over their ears, terrified by the sheer acoustic pressure. They were witnessing a machine that felt as if it was about to tear itself apart. But Marina did not flinch. Her hand was already on the control tube, her fingers wrapped firmly around the steel linkage. She was the feedback loop. She felt the surge of the engine trying to run away, the raw torque twisting the entire block on its mounts. She tightened her grip, fighting against the governor spring, manually forcing the rack back toward the no-fuel position. She was choking the beast. She forced the fuel plungers to rotate, cutting the volume of the spray. The engine fought against her, the scream dropping in pitch as she wrestled the RPMs down to a steady idle. She feathered the linkage, feeling the pulse of the injection events through the metal, until the governor's oil warmed up and the flyweights finally took command. The engine settled into a rhythmic, loping idle, the famous rolling idle of a Detroit. It sounded like a heavy machine gun firing in slow motion. The shed was now filled with the high-pitched whine of the Roots blower, a harmonic resonance that you could feel in your teeth. The white smoke had cleared, replaced by a steady, translucent heat haze. The block was warming up. The seals were beginning to swell. The engine was ready. Marina signaled to the facility manager. He hesitated, looking at the vibrating iron monster, then threw the main transfer switch. The contactor slammed shut with a bang that sounded like a shotgun blast. Instantly, the facility's full electrical load, conveyors, crushers, lights, hit the generator. It was a massive step load, enough to stall a modern engine that wasn't perfectly calibrated. The Detroit didn't even flinch. The governor sensed the drop in RPM before the human ear could even register it. The rack snapped open. A column of thick black smoke erupted from the exhaust stack as the injectors dumped fuel to meet the sudden torque demand. The engine growled, a deeper, throatier note, digging into its torque curve. It didn't bog down. It didn't hesitate. It simply accepted the weight. The lights in the facility flickered once, then burned with a steady, unwavering brightness. The frequency meter on the wall locked onto 60 Hz and did not move. The old iron had shouldered the burden that the plastic sensors had dropped. The silence that had been costing the company nearly $1,000 a minute was gone, supplanted by the industrial symphony of rock crushers and conveyor belts returning to full speed. The lights in the maintenance bay, which had wavered during the transfer, now burned with a harsh, unyielding intensity. The source of that stability was the screaming green block in the corner, vibrating on its skid with a violence that felt perilous, but was, in reality, the very definition of structural integrity. The 12V71 wasn't just running, it was dominating the load. It didn't care about the power factor or harmonic distortion. It simply converted diesel fuel into 60 Hz of pure electrical authority. Marina pulled a rag from her back pocket. It was already stained with the specific heavy grease of a 1970s machine, a combination of 30-year-old oil, diesel soot, and the solvent she had used to free the rack. She wiped her hands, not with the intention of cleaning them, but to smear the grime into a uniform layer. In her line of work, clean hands were a sign of unemployment. The black streaks across her knuckles were a badge of honor, physical evidence that she had touched the mechanism and compelled it to obey. She looked at the three technicians. They were standing in a semicircle around the running engine, maintaining a respectful, almost fearful distance. They were staring at the exposed rocker arms dancing beneath the valve covers, mesmerized by the sheer mechanical transparency of the process. They were accustomed to black boxes, engines encapsulated in sound-deadening foam and plastic vanity covers, where the only visible moving part was the cooling fan. Here, the entire valve train was laid bare. They could see the injectors firing. They could see the rack moving as the governor hunted for the perfect fuel rate. They were witnessing the internal combustion engine in its most elemental form, and it unsettled them because they had no screen to interpret it for them. "It's loud!" one of them shouted over the roar of the blower. "It's working!" Marina shouted back. She walked over to the silent Tier 4 generator, the $250,000 asset that had been neutralized by a $5 sensor. It sat there, immaculate, quiet, and utterly useless. It was a marvel of modern efficiency, designed to sip fuel and emit nothing but warm air. Yet it had failed the one test that truly mattered: availability. It was fragility disguised as sophistication. "Do you see that?" she asked the facility manager, pointing to the modern unit. "That machine is disposable. When its block warps or its electronics fail, you throw it away. It's an appliance. It has a service life of maybe 10,000 hours before the cost to repair it exceeds the value of the asset." She turned back to the screaming Detroit. That is a legacy. That engine was built on the infinite life cycle concept. It wasn't designed to be discarded. It was designed to be renewed. The block is merely a carrier for the parts that wear out. Liners, pistons, bearings, they are all consumable components. You replace them, and the engine is new again. That iron will outlive every single person in this room. The manager looked at the old machine with a newfound understanding. He had previously seen it as junk. Now he saw it as insurance. The modern world was obsessed with theoretical efficiency, squeezing the last possible drop of energy from a gram of fuel. But in the tangible world of heavy industry, efficiency is always secondary to reliability. Saving 10% on fuel is meaningless if the machine refuses to start when the grid fails. The Detroit burned more fuel, yes. It was louder. It leaked. But it ran. And at that moment, the difference between running and not running was the difference between profit and bankruptcy. The sensor on your new unit thinks the exhaust back pressure is too high, so it shut itself down to protect the catalyst, Marina explained, her voice cutting through the noise. It committed suicide to preserve its emissions rating. The Detroit doesn't have a catalyst. It doesn't have a computer to decide if it feels like working today. It has a governor that says, "If you provide me with fuel, I will provide you with power." That is the distinction between a smart device and a heavy machine. She began to gather her tools: the breaker bar, the timing gauge, the can of solvent. She packed them with the same deliberate pace she had used to diagnose the fault. She had no need to stay. The engine had achieved thermal equilibrium. The oil pressure was pegged at 50 psi. The coolant temperature was steadily rising to the thermostat's opening point. It would continue to run until its fuel tank was empty or someone physically pulled the shutoff lever. It didn't require a babysitter. She picked up the heavy, grease-stained service manual she had brought with her, the Bible of the two-stroke diesel. She walked over to the manager's desk and dropped it next to his pristine keyboard. The heavy thud of the book landing felt like the strike of a gavel. "Don't lose that," she said. "The new guy is going to need it when he discovers that you can't fix this engine with a software update." She walked toward the bay door, the sound of the Detroit scream following her. It was a harsh, aggressive noise, a mechanical howl that was an affront to modern sensibilities. But to Marina, it was the sound of a promise kept. The plastic sensors had failed. The code had glitched. The network had gone down. But the iron, the heavy, seasoned American iron, had held the line. The survival of the Series 71 is not a historical accident. It is the deliberate outcome of an engineering philosophy that the industry systematically dismantled decades ago. In the 1970s, a heavy industrial engine was a capital asset, a permanent installation expected to outlast the career of its operator. It is a philosophy that regards weight as a form of insurance. Today, engines are treated as consumables, designed with a finite duty cycle calculated to conclude precisely when the extended warranty runs out. The transition from repairable to replaceable was an economic choice, not a mechanical one. The Detroit diesel achieves a kind of immortality because it refuses to engage in this modern economy of planned obsolescence. Its longevity is structural, founded on the wet sleeve design, where the cylinder walls are separate, replaceable units, rather than integral parts of the block. A modern engine dies when its bore wears out. A Detroit simply requests new liners. It depends on a simple mechanical governor, a system that cannot be hacked, bricked by a software bug, or corrupted by a stray voltage spike. It relies on the sheer density of its casting, a mass of high-nickel iron that absorbs the kind of thermal punishment that warps lighter, more efficient aluminum alloys. Environmental regulations ultimately brought an end to the production line. The two-stroke cycle, for all its incredible power density and throttle response, could not meet the ever-tightening noose of emission standards. It was too raw, too honest in its combustion process, and it scavenged air with a violence that the EPA could not abide. The industry exchanged the million-hour engine for the clean-burning disposable unit, gaining purer air, but losing the ability to repair the very infrastructure that supports it. But while legislation could shut down the factory, it could not stop the laws of physics. The existing engines did not cease to run just because they were outlawed. They kept running because they were built to a robust standard that prioritized survival above all else. This leaves the specialist in a critical role. The modern technician is trained to read diagnostic codes and swap parts based on a flowchart. The specialist is trained to read the metal itself and to comprehend the intent of the original designer. In a world hurtling towards sealed units and black box diagnostics, the mechanic who understands the analog language of rack travel, governor droop, and injector height becomes a custodian of a dying art form. We are not just fixing machines. We are preserving the last connection to an era where human agency was more important than digital permission. The 12V71 in that shed is not just a generator. It is a monument to the idea that if you build something with enough mass, enough precision, and enough structural integrity, it doesn't have to die. It just has to wait for someone who knows how to make it breathe again. The heavy steel door of the maintenance bay clicked shut behind her, muffling the scream of the 12 cylinders to a dull, rhythmic thrum, but it failed to silence it completely. The silence is gone. Marina walked toward her truck, leaving the modern technicians inside to await a software patch that might never arrive. If you understand why heavy iron will always triumph over a plastic sensor, you belong here with us. Subscribe now to help us keep the legacy of real engineering alive.